Good. So it's a great pleasure to introduce teacher Kerner, which I know for some time now, maybe almost 35 years or more. And the first time that I came across not Richard Kerner, but his name was when I read Bryce DeWitt's paper of 1963 in Les Houches, famous Les Houches school about topology, gravity, something like that. And DeWitt wrote 200 pages. It's in the proceedings, so it's half of proceedings is the paper. Wrote in the proceedings a paper on dynamical theory of groups or something like that. And it appeared from 77, we just saw it. From 77, it asks to solve Kaluza-Klein problem, not for electromagnetism, but for Young Mills. And in 1967, we have that Richard Kerner solved it.
Yeah.
So,
but without reading the book, it was my supervisor Troutman who suggested me to do.
And Troutman suggested him to do, of course. Well, Troutman knew about DeWitt's question, and so to me, Richard is an idol. That first one to solve the dimensional reduction of 5-dimensional Kaluza-Klein in an extended group. Kaluza-Klein with Young Mills. And so, when I met him, I was very pleased in the middle of the 90s, or beginning of the 90s.
Yeah, but we started to work together.
And we worked together.
So. Yeah. Thank you so much. And I'm really pleased. It's not my first time. Later on, I had Portuguese students, and I just met them. They came from Coimbra. I was in Coimbra yesterday with my former students who are right now, they are both pensioners. Time passes by. When I took them, they were 20-something and I was 30-something. Very long time ago. So, thank you, Jose, for the invitation. I'm on my way to Brazil. There will be another workshop, and Jose was invited, of course, but he has such a heavy teaching duties that he could not come. But so we meet here. So now again, this is something that is very simple, and at the end I will suggest another problem that I didn't do it. I should have done it from the very beginning, but somehow it eluded my attention. But if some of you want to continue, that there's something to solve. I showed what next problem to solve. Now this one is how to generalize the Lagrangian. The observation is that the Kaluza-Klein theory, which is just 5-dimensional gravity, it is 5-dimensional Einstein's theory with Einstein-Hilbert Lagrangian, which is just scalar curvature. But in 5 dimensions, the scalar curvature has, again, how many degrees of freedom? In 4 dimensions, you have 10 degrees of freedom. In 5 dimensions, it would be 15 degrees of freedom. Still 5 more, because it's n times n plus 1 divided by 2. So 4 times 5 is 20, divided by 2 is 10. 10 components of metric tensor. Now in 5 dimensions, it is 5 times 6, it is 30, divided by 2, it is 15. So you get, in this 15, you get 10 normal degrees of freedom for 4-dimensional space-time matrix. And then 5 degrees of freedom. This 5 degrees of freedom, they divide into 4, which can be identified as vector potential, 4 vector potential, A mu, and a scalar field. We'll show how it works. So, but something that was not remarked for a very long time, I don't know why, is that there is a Gauss-Bonnet invariant this is just a resume. This abstract possibility of the use of static solutions is presented. That is the abstract. Now we go to the heart of the matter. So you see that in 5 dimensions, the Kaluza-Klein theory, of course, it was proved that it is not viable as for the description of even electromagnetic field, because there are problems with spinors. In 5 dimensions, it is not chiral spinor, so it is not a viable thing. And as we know, of course, the real thing is electroweak theory, which is much more degrees of freedom. It's not only 15, but much more. Even if we, because if we get out the gravitational field, what remains is just electromagnetic field and scalar field. It's not enough to produce viable theory of elementary particles. Also because it's thin. So, on the other hand, Maxwell's equations are very good, you know, that they describe very well the behavior of electromagnetic fields on macroscopic scale, but not in microscopic scale. Of course, when you go closer to the electron, closer to the sources, quantum methods start to be dominant, and of course they can be developed into series of powers of alpha. Alpha is this natural 1/137 and something, this natural parameter, and it gives a series of corrections to normal field, and this is the quantum electrodynamics. This whole science is very precise, it gives very good predictions, but on the other hand, one can expect that there is something like effective field theory. If you sum up all these things, it can be in some condition, namely also for static configuration, may be replaced by what is usually called effective field theory. Just postpone the series, postpone the quantum effects. If it is far away, you can still have something that is looking like effective nonlinear electrodynamics. And this idea of nonlinear electrodynamics started much long before quantum field theory, of course. It was in 1912, and in 24 already, but they still didn't know much about quantum mechanics. They knew about quantizing of atoms. Anyway, it's 34. Of course you're right. Yeah, 34. Sorry. Yeah, 34. Of course. In 24, it was still in Poland, and sorry, I will correct it. 34. But me is 12. Me is correct. Yeah. So they were not convincing because they produced a Lagrangian for electromagnetic field that is very specific with the square root. It's a very complicated function. And the idea was to get something like limiting value of any field, that the field cannot go to infinity, but it is a little bit like in relativity. You have this factor 1 minus v squared over c squared, so v cannot be more than c. So there was something like that. It was just pure electric field. It was under the square root 1 minus e squared over e0 squared. This e0 was like speed of light, and so you cannot have the field E more than some. But of course, it's very nonlinear, and so of course it was still. But what is also characteristic that it does not use the second invariant of electromagnetic field. This is an invariant of electromagnetic, relativistic invariant, which you know, and this is the usual Lagrangian of divided by 4, but it is the Lagrangian of electromagnetic field, Maxwell's theory. But there's another F mu and F dual, which corresponds to E squared scalar B, It is also a relativistic invariant, but of course you cannot use it for the simple reason because it is not a scalar, it is a pseudoscalar. Okay? But the square of it, you could use it. Because the square of it is a real genuine scalar. But it will give nonlinear equation. So now the observation is that in four-dimensional, there is something that is called Gauss-Bonnet invariant. This is curvature invariant of second order. The scalar curvature itself is invariant, but of first order, just proportional to Riemann tensor. This is a combination which is proportional to Riemann tensor squared, but you have three independent things: Riemann tensor squared, or Ricci tensor squared, or finally scalar curvature. It turns out that they are not all independent. In 4 dimensions, you see that this thing, if you compute it in 4 dimensions and insert into variational principle, you get nothing because it is an invariant. It is a topological invariant. SR itself is a topological invariant in 2 dimensions. There is no general relativity in 2 dimensions because if you put R as a variational principle in 2 dimensions, then you discover that the total integral of R is just, if it is a closed space, it is just 4 times pi for Euler characteristic. That's it. So it is invariable. And if you make variation, it is 0 because there is nothing to do. But in 3 dimensions or in 4 dimensions, Riemann scalar gives you Einstein's equation. The same here, up to 4 equations. This thing is total divergence, and it does not contribute to the equations, just an invariant. But in 5 or 6 dimensions, it contributes, it gives something, modifies the equation. So that means that even in 5-dimensional Kaluza-Klein theory, one could add this, not only use the usual Einstein-Hilbert Lagrangian, but add this part. So this is the starting point. But now, if we add this part, let us compute what does it mean in terms of electromagnetic field. Because, of course, it will be very complicated interaction between gravitational field, electromagnetic field, and eventually even with scalar field, if you let it go. But we'll do something pure electromagnetism in 5 dimensions, starting from Kaluza-Klein. So that's very simple. This is the Kaluza-Klein ansatz, but without scalar field. You see, there is something usually here and here. One could put it here. One could put G phi, which is also can be a function of space-time. Kaluza-Klein, they did, this is, some people say it was a Kaluza-Klein miracle, because in principle, if you start with something that is already squeezed because you have killed 1 degree of freedom, normally it has to give you how many equations? 15. Yeah? But now you killed 1, it will give you only 14. 10 for gravitational field and 4 equations for this. But it will be a over-constrained system. Somehow, miraculously, it works. It is a solution, even so. So this is a small miracle, because without that, they would not solve it. Right? So, again, another little error. Sorry, forgot the anti-slide. Okay. So let us compute, and the computation is made very easily in a non-holonomous system. It is not just 5 different coordinates. You have 4 coordinates of 4-dimensional space-time plus 5th coordinate. But here, the best thing is to use this. This is a non-holonomous because it does not commute, but nevertheless. So this is the basis, and in this basis, the computation is easier. So you get something like this. This is the And of course, R mu, how many? These are 20 different, remember, 20 different independent because of symmetry of Riemannian tensor. Now, here you have 4 times 16, and here again 4 different components. All in all, again, one can compute how many components you have in a Riemann tensor in 5 dimensions, much more than 20. So these are the computations, and then we can compute everything. Not only the scalar, here is the scalar, here is the Ricci tensor. The Ricci tensor also has ordinary 4-dimensional part, mu and 5, this is the mixed part, and finally the fifth 5 dimension, which is open. So all together gives you fantastic. This is the result. This is Kaluza-Klein. It gives you just the Lagrangian of Maxwell's theory. No gravitational field, no scalar field, just it. Okay. Now, as we said, we can compute also Gauss-Bonnet invariant. So if so, of course, F means this, and so now the new Lagrangian will be the old Lagrangian, and this Gauss-Bonnet invariant. I will put some dimensional factor because this I2, the Riemann tensor, its dimension is centimeter to -2, 1 over centimeter squared. But Gauss-Bonnet invariant would be 1 over centimeter to the 4th, because it's quadratic. So you have to compensate. So this is 1 over centimeter squared. It's just to compensate. Okay. And then we compute it, and here's the result. As could have been foreseen, it is 4th order in F mu. R, the first invariant, Riemann scalar, was of 2nd order in F mu. This is in 4th order. But what is amazing, as we said, it does not give any higher order equations because it is still depends only on first derivatives of potential. It depends on F mu, not on derivatives, which is not that obvious. You remember, look, there was something here, for example, that depended on the derivatives, first derivatives, so there are second derivatives, so it could have been, but somehow they are also eliminated and no problem. So this is it. And now, from now on, to understand better, I will translate everything into fields like we use when we study electromagnetic field, E and B. So this is, again, the equations of motions will be like this. If there were no these extra terms, without this extra term, you will have this usual Maxwell equations. And of course, these equations are always satisfied the Bianchi identity because F mu is the full differential. So these are always the homogeneous without sources equations. They are always satisfied by definition. And these are the equations of motion, which can have, the sources on the other side, for divergence. And we have something else. Now let us translate it into common language, high school. So this is the Lagrangian. You see that the Lagrangian contains the usual one, or it should be maybe divided by 2. No, this is the, this is good, 1/4 of F mu, but because of symmetry, you get twice the same thing, so it's 1/2 there. And you have this extra term. Extra term, as we could foresee, it is the other invariant, E times B, but squared, of course. So the only thing that gives you this, that brings this 4th order thing, is just this small, as we could foresee. Nothing. Of course, it could have been something worse. It could have been this to the square. That would be a mess, but it is not. Kaluza-Klein gives you just very, very simple thing. So the equations, if you write the equations, you get, of course, as I said, these two equations, this and this, they are sources. This is d mu f mu nu, this Bianchi equation. This is always. And the equations which are usually with divergence and rotation of H, I introduce H and D and E like it should be. So they contain something. So it's really interesting. Even now we can get something, a very important information. The important information is that suppose that we look for solutions in which E is orthogonal to B everywhere. Like, for example, in plane wave, it will be a solution. Because if this disappears, what is left is just normal Maxwell equations. You see, if E times D disappears, what is left is just divergent D sources is 0 and rotation just Maxwell equation. So this means that the plane wave will be also a solution. Not only it will be a solution, but we'll compute the energy, and we'll see that it is stable because any deformation of it will bring energy up. So it is even plane waves are solutions of this theory too. So now I just in vacuum H and B is the same and E and D is the same. So I have only E and D from now on. So I wrote. So look that these things behave. This behaves like the charge density. The divergence of electric field usually is compared to density of charge, rho. And this rotation D, this is called the displacement current, and this is just also behaves like current. And I can show that this induced, again I wrote the same thing. So of course, if there were extra sources, they should be rho should be added here, and J, the current density, should be added here. But we don't need them because this nonlinear thing behaves like a source of its own charge density, the source of its own current. This is the induced charge density in this time. So it just, and they are conserved. For example, we just take the d over t divergence E, and we get this expression. And then I take divergence of d over dt, see? And I get another expression. And if I compare the two, I use some vector calculus. Comparing the two, we get the conservation. So the induced current and induced charge and induced current density, they just satisfy the continuity equation. So you don't need charges, you don't need, this was Einstein's dream, by the way, that everything can be explained by field. No masses, even masses that are just singularities of the field or something. But here it is true, it's like this. So we have, of course, this conservation. And now let us see what energy means. Energy is, if we take this combination and substitute the new equation, what we get is this. If there were no this term, it would be, again, this well-known conservation law, which is the energy density and pointing vector. The energy density, the derivative over time of energy density is the same as divergence of pointing vector. But here we see that we have this extra term, so the energy is not the same. The pointing vector is exactly like in Maxwell's theory, but the energy density has this, well, it would be really strange if everything were the same, so there must be some difference. So the difference in the energy. And as I said, if you put E orthogonal to B, like in plane wave, then it would be exactly like a plane wave. And then you see that if ever you depart from E orthogonal to B, the energy rises. So it's all positive. I mean, of course, the epsilon, this should be positive. So we will set epsilon 1 to make it stable. If epsilon was negative, then it would go down and so we take this fixes physically that so we can forget the epsilon. So this is by the way, one could also compute the energy momentum tensor canonically like this and get exactly the same result. So now these are still general properties that I told you. This wave, plane wave is a solution, and okay. Yeah, this is what I said already. Pointing vector. So we write now another thing. Let us start to look for static solution. Is it possible to get something, a configuration like a soliton? How much time do I have?
Yeah, just like 15 minutes.
Oh, okay. So is it possible to get some configuration that would behave like solid? Something. Okay, why not? Of course, we kill all d over dt. So what is left is just this. This is, of course, like this, rotation. And these are this extra density of charge and density of current induced. Now, what are we looking for? First of all, E and B should be there. Should be symmetry in some way in E and B. Now, what we are looking for is kind of easy to foresee. We want it to look from far away like a charge, but not only like a charge. B, what B can be. B should behave like because divergence of B is still 0. So lines of force of B should be closed. And electric field can go like this. So what you are looking for is roughly something that will behave as seen from far away, charge, and magnetic dipole. Even if we did not know about the existence of electrons, like me, for him electrons were just charges. But from here you see that charge alone is not enough. You have to have E and B. So this is, and J also, the current, this induced current, also has to be closed, because if it went out, you have no d over dt. So the divergence of this must be 0. So if divergence, it behaves like something like rotational, also like it. But it has to be perpendicular to B. Because if B is like this, the current should behave like toroidal time. Okay, so this is what we foresee. And of course, this is symmetry. If you look at how it should behave. So the current is supposed to have only azimuthal component. The B and E should have no azimuthal component. They should be the same whenever you cut like this along Z and any axis like here, because phi, it should be completely equivalent. So any plane like this Z, Y, or ZX, or whatever in between, should look exactly the same. So no dependence on phi, but dependence on rho and Z, cylindrical coordinate. So if it should behave like, if you want it to behave like electric field far away, and like a dipole field, it's easy to see what kind of symmetry it must have. It should be like this. When you go from this direction down, E should change the sign. E goes like this here, goes like this here. But B, no. B should not change sign. because B is like this and like this, so this component, the Z component, behaves like this, whereas the rho component changes time. And the rho component does not. It has different symmetry. Again, this is the symmetry you can foresee. And again, now let us suppose that we are far away. So what we want to see at the zeroth approximation, very far away, we should see electric field. This is in cylindrical coordinates. So electric field should be shaped like this. This is the total charge, and B, magnetic field, should behave like magnetic dipole. So this is now the idea is this is we called it B0 and E0. We feed it into equations, and we see the Maxwell equations will be satisfied, but then we have some extra, and we see how this extra behaves. And this is what we discover, that the next approximation, what we see far away, is extremely, look how it falls down. So the charge density falls down. First, it falls down like Coulomb field. This is what we suppose. But the next approximation, the next term that comes from this nonlinear equation, behaves like R2 minus 9. And the same, the current density, R2 minus 8. So you see how it falls off. So far away, you see really only dipole. Only when you come closer, it starts to default. Now, the best thing to do is to use toroidal coordinates, not just the toroidal coordinates are also, they have this pi angle, but then they have two different parameters, mu and eta, and this is the substitution from cylindrical coordinates to toroidal coordinates. Okay, this is how this constant, of course, in pi, it's exactly the same everywhere. Does not depend. Pi is symmetrical. And constant eta. Eta goes like this because a torus has two angles. One is like this, another is like this. So eta measures this angle is phi, trivial, just like in cylindrical, the same. But then you have eta, which is the angle along this toruses, and mu is kind of gives you the scale. The A is the absolute scale, that's the number, right? Then it becomes a little bit complicated, but at some point you discover that the vector potential can have only one component. There's only one component, the phi component, because B and E, you want to have them no phi component. So this is, it should be only phi component, but depending on these two coordinates. So you'll have E and B in these planes, independent of phi. So there you go. So here it becomes a little bit more complicated. It's a substitution to make the thing simple. You discover that you can somehow separate the variables. So the dependence on eta is kind of canonical in this coordinate. If you suppose that the field B is just along this constant mu lines, along this turbulence. And then what is left, only the function, how it depends on the distance, which is just this function. Okay, then becomes just computation work. It is a little bit heavy. I did it. You can do it. One. And this is the result. Now I just copied it because I published this first paper was published in '87. So it is 35 years ago, 36 years ago. And I made a mistake. I published it in Proceedings of some Varna Bulgarian conference. So it was like putting it in, at that time, archive didn't exist. So it's like put it in a black hole. Nobody could see it. Nobody. It was never sighted ever. So I was recently. I said to myself, "Come on, it's just stupid." So I because it was typed by our secretary at that time, and she did it by hand. Everything, all the. So these are the original illustrations she made by hand, and she typed it in IBM machine. You know that you probably never saw them. You're too young. There were IBM machines, typing machines with balls. You change the ball. It was a ball that was going like this, and you change the ball for mathematical signs, another for Greek letters, and also had to change the ball. And absolutely work of terrible. Her name is Josette Durand, and she made this. So this is roughly, this is how the electric field should behave, see, like this. This is how B eta, the eta component of magnetic field behaves. This is how E eta behaves, and this is how the scalar product of the two behaves in functions of eta when you go around. And then you compute the charge density and the current density. This is what is in the intermediate computation. It's all factor of eta. You go like this. And of course, the intensity changes when you change the distance, because the circles become bigger. And this is finally the chart. And when you put it all together, figure, I'll show you what comes out of it, all done by hand at that time. I had no Mathematica, no Maple, still 87, just before. Well, I wrote it, it was published in 87, I worked on it in 85, 86, still no such thing. And this is what gives, once you put together all these dependencies, you discover something very funny, that the charge density, that there is this A thing, this is where the singularity of this coordinate system is along some circle in XY plane, Z equals 0. And you see that there is something that is discovered, that is kind of polarization of vacuum. Because if you have the positive concentration of, if most of the charge, positive charge, is concentrated around the axis, then around you have this and this and this negative. So you have the opposite charge. That doesn't mean that the total charge is 0. No, because this cannot overweight. Of course, it goes down, 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 but roughly it behaves like this. It is just if you put together all these curves and make out. Also, what is funny, also the current behaves, of course, it goes, if you try to interpret this current, that it goes like this, it has only 5 components. Then you discover that it is equivalent to this charge density going with the speed of light. There's only one parameter here, the speed of light. So it's like, but in Dirac's equation, you get the same result. The electron goes with the speed of light. Only the average is not the same because of, but the only parameter in Dirac's equation is also speed of light. And then what we discover also, it's very interesting because you look at the solutions and you see that if you have one solution like this, then you have 3 other solutions, because whenever you change E to minus E or B to minus B, the equation will be satisfied. So this means that any solution, they go in double 4 types of solutions. You can change, suppose that we started with this solution. There was some finite energy, finite charge, finite magnetic moment, and finite spin, because you can compute also the kinetic momentum of this. and there, it's not zero because you have pointing vector. Pointing vector is the kinetic. And then you see that you have 4 states. One is minus b, so it is the same mass, the same charge, but magnetic momentum is inverse, and the spin is inverse, the kinetic momentum. And then you have something that is, again, you change E but not B. You have the charge is opposite, and magnetic momentum is mu or minus mu, but it is opposite the spin. So what we see here is that there's an electron in 2 states, spin up and spin down, and magnetic momentum along the spin. This is the electron. And then we have something that is opposite, which we call positron. So the result, without Dirac equation, but of this, it hints you that there must be something like this, that these solutions behave like Dirac's electron. You have 4 different components and 4 different states. And again, they have still
A few minutes.
a few minutes, yes. Well, okay, this is parallel, anti-parallel, very easy, yeah? We have this conclusion. Now, the bad news is that still it is not, you cannot have a really non-singular solution. It's, one can show that although the singularity is not as strong as Coulomb singularity, 1 over r, still it is a logarithmic singularity. By the way, that is what gives you also quantum electrodynamics. There is Weisskopf's paper when he computed the polarization of vacuum. It was still in, I think it was before the war. And he proved that with polarization of vacuum, instead of getting Coulomb, you get logarithmic singularity, but still it is singularity. So here it's roughly the same. I want to show why there must be singularity. This is application of Poincaré's lemma. Poincaré tells you that if some is divergent, the hypothesis of Poincaré's lemma is the following: that you have something that is has topology of R3. There's no holes, no singularity, just everything on R3, well defined. No holes, no Dirac string, no nothing. Yes. And then we can prove that if divergence of a vector is 0, then this vector is a rotation of something. Divergence of a rotation is 0. If divergence is 0 everywhere and the topology is just that, then this thing is a rotation of something. The same here. If rotation of something is 0, then what it is? Gradient. No, gradient. If a rotation of something is 0, that means that you can replace it by a gradient. So let's do it. Supposing that there is no holes, no time. So okay, so we'll say that this is rotation of something, and this is a gradient. Okay, now everything is supposed to be smooth. This is again rotation. I compute it, and I can replace it by this, and this I replace it by divergence. So we have 2 divergences. One is divergence of some potential multiplied by rotation, a rotational field, and another is divergence of some scalar field multiplied by b. I put them together, and I see that E squared plus B squared is equivalent, under these assumptions, to divergence of something. Fine. If I have something that is a divergence, I can integrate it over whole space and look how it behaves. Okay. So this is, I will do the thing, but now we remember what were the assumptions about our solution. B and V have to behave like electric, far away, like electric charge and magnetic dipole. So I know how they fall off. So I insert this, And I see that the whole thing, the integral, behaves like 1 over r. So if I go to infinity, it vanishes. But if it vanishes, then this thing must be 0, because it's positive. This is what I integrate, right? So there is something that is not right. Either it is not, either it is 0, so there is no problem, or if it is not 0, it's like with Coulomb field. I mean, if you compute, you get divergence, everything 0. But because of this, if you close it, then it's no more 0. But that's because there is a singularity. It's no more R3, but it is R3 without the point. So here the same, of course. This is possible because there is a singularity, and the singularity is on this page. So this is the. Then again, this I will skip because these are computations trying to compute really the solution. I'll just end up. We have to make substitutions. A lot of just to. I'm showing up. I mean, it was hard work. And then finally you get Morse and Feshbach, you get the book, you see there are Whittaker's equations, you get this series of solutions, there are Legendre polynomials of one kind and of another kind of cos mu, and then you see that they, indeed, these things, they have singularities. One has singularities here, another there, and you cannot make it without singularity. So this is the, and green function would be the same. And now I'll finish. This is a student of our common friend, Dima Datsov, who is a Russian, who is working in. And recently, she published last year, he published a paper with his students. They made also nonlinear, but not electrodynamics, but just full thing with electroweak. And they computed how they also looked for static solutions of electroweak combinations, which is much richer. And of course, they used what I could not use at the time, computer and very hardware. And they got the solutions numerically. And look what they got. It looks like what I got. Remember, this thing, vertical close, and then all the way around this toroidal thing. So it is kind of, I don't know what to say. That you don't need that much of technical things or these computers to arrive at some conclusions that you can get from computers. On the other hand side, of course, I could not do it with full theory, electroweak. It's too complicated. 5 dimensions is okay, but more it would be really. And then final word is that you notice that all this, I switched off gravitational field, pure Kaluza-Klein, 5 dimensions. But I switched off not only gravitational field, but also the scalar field. So it occurred to me that if you put a scalar field in and compute again the Gauss-Bonnet invariant, perhaps we will get something of 4th order, not only 2nd order in pi, but the 4th order. And I bet that it will be the fixed potential, but one has to make the computation. So I invite you to do it. Thank you.
Thanks very much for the great talk, and also perfectly on time. Do we have questions?
Well, because I skipped the calculation. But everybody can do it. It's not a problem.
All right, so yeah.
The last thing, why you have this potential, you put the scalar and Gauss-Bonnet, we couple the scalar with Gauss-Bonnet. What happened? No.
Like the first, how to come to the first
But
pages.
you have to, I mean, go back all the way. Sorry.
Okay. No, this is Gauss-Bonnet. in 5 dimensions. But what I did, this was a substitution. One here and nothing here. When you put the scalar field, this is here, scalar field is equivalent with G55 component. So it is here. Usually it is replaced by E to phi or something, but because it has to be positive. So it appears here as a factor, here, here, and here. You put it in, and now you have all degrees of freedom. And then you have to compute again, not only like what I did, but, and of course, because this Gauss-Bonnet is of 4th order, you remember, so you get something that will be of 4th order in phi. 2nd order, of course, and 4th order too. How it will, I don't know, but perhaps maybe you'll have also the square instead of d mu phi, you get d mu phi squared, probably something like that. Well, one has to check. It's not big, but it could be checked. Could be interesting.
More questions?
So, what born info, essentially, kind of born info.
No, born info is absolutely. Born info is like this.
But you have the same invariant. Right? You have the same invariant. It's square minus square.
No.
Square root.
No. Born info don't need they don't use this. So that it is born info is like this. Minus or plus. So it is terribly nonlinear. Of course, it is 1. I think it's like this, minus and minus. So if you develop it, if this is small, you develop the whole thing, 1 will go. And this was the first time we did, maybe it's 1 part or something. But the whole thing is terribly significant series. And it does not contain the second invariant. So it's completely different. It's not born info. No. Born info is based on this. And this is the idea of also E, because if you put some constant here, and if this is replaced by electric field only, then it means that there is some limit value of the electric field. Because if not, it becomes magic. So this is good. No, born info, completely different thing.
You get the line singularity.
Yes. Yeah. Unknown singularity.
It's like curve.
Yeah. So, yeah, the same thing. Yeah. Whenever probably it is some universal thing. Whenever you go to cylindrical symmetry, more or less you'll get something. In spherical symmetry, you will have it in point. Cylindrical, you must have, there is nothing origin, but you'll have the singularity on someone. This replaces Dirac string or something. Yeah, but you can see that this Poincaré lemma is quite powerful. It tells you that either it's 0, or you must have something that topology is not just like topology. It's something that feeds your possibility of motion. Here, not simple topology. That's it.
What about if you put the gravitation? Well, we'll draw it from the plan.
Yes, of course. No.
First of all,
First of all, gravitation and resonance. We made it together. No, we made Huh? 98 units. No, but it's no, but there the problem was more the propagation. Linear propagation. That is also interesting, but no solitude. No. No, there's plenty of things. What I would do at the time, I would make the computation with the scalar field. See what does it imply. Probably there was no, I think it's not true. There won't be fixed potential. No. So it all depends on derivative. It will be something like d-5, then some term d-5 squared. That's good. Now, what kind of theory is that? No. But maybe it will help us to, maybe one singularity will fill another, you know. Maybe it helps for Orion worse. I don't know.
No questions?
Okay.
If you enjoyed the video, like and subscribe.